Okay, and so the key is there is a reference. So this is our reference motion or reference trajectory. And the way this trajectory comes is, well, we've seen many ways. One is we specified polynomials. We use the trap well traj in Matlab. You could do this by optimization, which we did last class, or you could use RML pause, which we saw in copylescent, right? That's reference. Now we want to track that reference. And then our controller is probably going to have some error, or it's going to do a great job. So what makes this tracking hard is that there is, so this is the tracked reference. So the challenges here are sensor noise. There could be external disturbances. Okay, there could be modeling inaccuracies. Okay, there are other things, but these are the three most important things which prevent us from tracking the system perfectly. So in that case, what you need to do is you need to look at the error and then use the error, or it's the rate of change of error, to find a controller which will ensure that the tracking is reduced to close to zero, right? So in case of manipulators, we've seen that, or links really, link systems, we've written the equations from Euler Lagrange. Equals Qj. Okay, so when you take this equation, that is the Euler-Lagrange equation, and then take the derivative, you end up with equations of motion, and these equations have the same form. Okay, the form is the mass matrix times theta, but theta is in brackets, theta double dot plus C theta dot plus G. I'm missing something there. There'll be C theta dot times theta dot, that's the Coriolis and centripetal terms, and then G theta equals torque. Okay, so it's the same form. Okay, and so given this form, we can then ask ourselves, how do we apply torque such that the system is tracking a certain reference? So that's the goal. How do you set this torque? So what I'm going to do is I'm going to motivate this form with the simplest possible example, which is a single degree of freedom system, which is basically a spring mass temper, mx double dot plus cx dot plus kx equals f. Okay, this is the simplest one DOF system. This is not a manipulator clearly, but it is an approximation of the manipulator when it is moving over delta theta. And in that case, you can actually write down this as a spring mass temper system. If you think of it, if that's easier for you to think about. Okay, so we have the system, which is a spring mass damper system, and then we want to understand the system. And understanding the system, I'll show you, will then help us to control our end-link system very easily. Okay, so let's talk about the system. So let's take the first case of an uncontrolled spring mass damper system. Okay, for the uncontrolled system, we'll have equations in this form. So here the force, external force, is 0. And then what we'll do is we will divide it completely by m. We have Okay. And now what you can do is, this is, if you remember vibrations, then we can define what is known as the damping factor, which is defined as, well, it's basically defined by first defining natural frequency. Natural frequency is defined as K divided by M, this way. And then the damping is defined such that it's equal to the damping term times omega n equals the middle term, which is C divided by M. So you can use this equation. So we've taken these. So although there are three variables here, C, M, and K, we really are looking at two numbers. And these numbers are C divided by M and K divided by M. So it doesn't matter what M is, as long as K divided by M and C divided by M is the same thing. So once we have these two numbers, we can replace these two numbers with two other numbers, the damping factor and omega n. And so this is totally equivalent. It's not like we have reduced three numbers to two numbers. That's not the case. Okay, so we have these two numbers, and then we can write these two numbers now from these two equations as omega n equals square root K divided by n, and the damping equals C divided by 2 square root mk. Okay. Now, what we can do is we can try to understand the behavior of the system for different damping terms. In fact, there are three regions. Okay, so we take the system, spring mass damper system, we perturb the system. So let's perturb it, say some condition x 0, and then let it go. We'll see that there are three distinct responses. One response is a lower shoot and keep doing this till it dies off to 0. This is 0, by the way. This is x t. The second type of response is it's not going to overshoot, but it's going to be something like this. Okay. It's ultimately going to 0, but it's going to take a while to go 0. And then there's another response, which is it's going to 0 in a shorter time. Okay. Now these three responses have got a name. This one is called underdamped system. And that happens when the damping factor is greater than 1. The blue one is overdamped. This happens when the damping factor is greater than 1. And then the green one is called critically damped, where the damping factor is equal to 1. From these three responses, you can see that, yeah.
I think you just made a small error in your inequalities. Underdamped should be less than 1, no?
Right. Good catch. Yeah, sorry about that. Okay, so then of these three responses, you can see that the response which goes to 0 the quickest is the critically damped one. And so what you want to do is you want to essentially try to get that spring mass damper to go to 0 as fast as possible. Why 0? It's because if you can think of 0 as some kind of an error, then you want the error to go to 0 as quickly as possible. So this is the ideal scenario. Okay, now for a system like this, where there's no force and you're trying to make the system be critically damped, you don't have much choice but to change the C, M, and K, put them in the right way. In fact, if you want the damping factor to be equal to 1, then you can see that from here you can write C equals 2 square root mk. So as long as so if you're given a mass and you're given a spring constant, then it tells you how to choose C, or in other words, if you're given a M and a C, it tells you how to choose K, and so on. So you can physically design the system such that it is critically damped by following that formula. Okay. Now the question is, you don't have the luxury of designing the system physically when you're doing control design. You better do it in controller. So what we can do is now we can actually use this force, which I put 0, in order to control the system to be critically damped no matter what. So you can choose whatever C you want, whatever M you want, whatever K you want, and I don't care. What I'm going to do is I'm going to show you how to control this force. We'll not set it equal to 0, we'll set it to a different value such that the system will always be critically damped. Okay, so now we take the controlled case. Where we have mx double dot plus cx dot plus kx equals f. Okay, we will choose f to be minus kpx dot, sorry, kpx minus kdx dot. Okay, and kp and kp are constants. In fact, the user chosen constant, and I'll tell you how to choose them. So this is our feedback controller. It's a feedback controller because I need to measure x in order to find f. I can't do it without a sensor which would measure x. So now let's put this in that equation. Okay, now we'll rearrange this a little bit. So C plus KD x dot plus K plus KPX equals 0. Okay, now what we can say, we want this to be critically damped. So what is the damping factor? Well, the damping factor is C plus KD divided by 2 square root m times the last term, K plus KP. Okay, all we need to do now is to make this equal to 1. And so we can now write this as 2 square root m K plus Kp. Let's square both sides. That will be 4. Okay, so we can expand that out. What we'll do now is, remember here, what we're trying to do is, we are trying to find Kp, Kd, such that we have critically damped system, right? So those two are unknowns. Now, if you look at this equation, you have two variables here which you can control. This is one, and this is the second one, two variables. So we have one equation and two variables which we can control. So clearly we have ample choices here. We have infinitely many choices because there are two variables in one and one constraint. So what we'll do is, instead of, so we'll sort of solve one equation, solve for one constant in terms of the other constant, and then we'll basically have a family of solutions based on that. So what we'll do is, we'll try to solve for KD because KD appears as a square. So let's write this equation as a quadratic equation in KD. So KD square plus 2KD times C. And then I need to write everything else but involving the constant. So C square minus 4mk minus 4mkp. So now if you refresh, the way to solve a quadratic equation is KD equals minus the middle term plus, sorry, minus the middle term, which should only be the constants, not KD, which is a variable, minus the middle term plus or minus the square of the middle term, which is 2KD, sorry, 2C square, minus 4 times the first term, which is 1, times the last term, which is C square minus 4m k minus 4m kp. Okay, so sorry, and then you should divide it by 2 times the first term, which is 1, so 2. So if you solve this equation for the two roots, you get minus c plus or minus 2, sorry, there should be 2 on the outside, and then there'll be m k plus kp. Now, these two roots are, one of these roots is going to be negative. If you take the negative sign, then we have c is, the damping is always positive. So this term, the one with the negative sign, is only always going to be negative. And we know that if you have a feedback controller, which is a positive negative feedback, then that's going to just blow up. So we have to ignore that solution. So the only solution which works is minus c plus 2m. Okay, so this is our solution. What the solution is telling us is that if you give me kp, whatever, you can fix it to whatever value you want, it will in turn tell you what kd is. You cannot choose kp and kd independently. Either you choose kp and then find kd from this expression, or vice versa, find kd first, assume kd first, and then find what kp would be. Okay, so that is our equation for critically damped. Or in other words, it's going to go to 0 in the fastest possible way. Okay, so I'll show you an example in Matlab. We'll put m equals 1, c equals 1, k equals 10. We'll put f equals minus kd x minus x dot minus kp x dot, which will give us kd equals, so using that formula, it gives us minus 1 plus 2 square root 10 plus kp. And then we'll start the system with the initial condition x of 0 equals 0.5, x dot of 0 equals 0. And then we need to make a plot, well, simulate the system and make a plot of x versus t for, so it starts at 0.5, okay, and then we'll do this for different kps. Okay, so choose a kp, put it in this equation, get a kd. Let's call this 1. So choose a kp, put it in the equation 1 for kd, get a plot, do the same thing for a different kp, and just keep doing that for increasing kp, then see what the response can be. I'll just show that example in Matlab. Just there's a main file, there's a right-hand side file. The right-hand side file basically gives me integrates the equations, okay, given a kp, kd, and the parameters, and then I use ODE4 for this. Okay. So what I did was initially I set the kp to be, let's say, 1, okay, and then kd comes from the formula I wrote down, right? And so let's simulate the system with 0.50 as to be the initial condition. Okay, so this is a plot of position x versus time, and you can see it takes about close to 3 seconds for the system to go back to 0. Okay, now you can change this. If you change this to some random value, not the critical ones, you'll always see the response takes more than 3 seconds. So for example, if I put kp equals 1, kd equals 0.1, okay, you can say that's critically overdamped, sorry, underdamped. If you make it maybe 2, this is also looks like it's overdamped. 10. Okay, so that takes more than for 3 seconds, so it's overdamped in this case. So you can try different values for kd for a given kp, and you'll see that you cannot beat this value of kd when it comes to response. So we've seen it takes 3 seconds with a kp of 1, which is the only free parameter now. Assuming that we're going to fix to this particular form of kp and kd. Now let's change this to 10. Okay, factor of 10 change. Now you can see that the response takes about 2 seconds to get to 0. And then you go to 100. And then you see that it's less than 1 second. And then 1000. And then you can see it's probably less than half a second, and then we can keep ramping up and then see what happens. So here it's very close to 0. Okay, now I think beyond this it's actually not going to go any lower, but it's going to blow up. That did well actually. It's still 0. You can zoom it here probably. Yeah, it's going to 0 very quickly, and I think it blows up here. Okay, that worked. Okay, this is what I expected. So it became 10 raised to 300, and that's because what's happening here is I have the integration tolerance to a certain value, and if I go, if my gain increases beyond that, then it's going to basically get unstable. So this instability is a numerical instability due to the integrator. If I have a better integrator, it can actually handle this. On a real system, you cannot have a high gain because you invariably have noise. So your noise is, let's say, order of 1e negative 3. So at some point that 1e negative 3 is going to get multiplied with a gain of 10,000 and become like 1. And that's where you'll realize that you're getting, instead of canceling the errors, you're actually amplifying the noise, and then you will have an unstable system. So this limit is basically set by your system, typically the noise, and sometimes even the disturbance and modeling error. So this is just an illustration of what you can do with a simple system and have an intuition about feedback control. So let's say extending the same idea just to 2D. Okay, so in general, a two-dimensional system is best written in terms of a matrix. I'm going to write it as a matrix: M11, M12, M21, M22. Plus we have the damping term, and then we have the constant term. Okay, so this is the simplest two-dimensional system with not making any assumptions about the diagonal terms. Now, if we take the same idea, we can say that the F1 and F2, which are the forces or the external forces which we can use to control the system, will look something like this: KD11, KD12, KD21, KD22, x1 dot x2 dot minus kp11, kp21, kp12, kp22, x1, x2. Okay, so now we have, so for one DOF, we have two unknowns, kp and kd. For two DOF, we have basically, if you can count here, 1, 2, 3, 4, 5, 6, 7, 8. So 8 unknowns. The KP matrix, which is 2 by 2, and then the KD matrix, which is 2 by 2. Okay, so you can see that for 2 DOF, we have, since we have 8 constants, we need to generate, in this case, we'll have to generate 2 equations. So in this case, we have 1 equation, and that equation was related to 1 damping constant. Here we'll have 2 equations corresponding to these 8 unknowns, but then solving for those 8 unknowns from 2 equations is going to be a nightmare, because you'll have a family of solutions, and it's just so hard to find solutions, these families of solutions, and then how do you choose one set of solutions for a scenario is just a nightmare. And so trying to extend this idea of one-dimensional to two-dimensional or n-dimensional is just not worth it, because it's going to involve so many constants. So I'm going to show you what people do here. In this case, they use a trick which is known as, we call it, there's different names for the same thing. It's called control partitioning. Okay, sometimes it's called computed torque control, and sometimes it's called feedback linearization. Okay, I think there are subtle differences between all three names, but for the most part, they are almost the same. Okay, they're called by different names, but they do the same thing. Okay, and I'm just going to motivate this with more complex example of a n-dimensional manipulator, which is more general than this. This is just a linear form. I'm going to take the nonlinear form. So if you have this equation, plus c theta dot plus g, sorry, always miss this term, theta dot plus g theta equals torque. Okay, now what control partitioning or feedback linearization or computed torque control does is it starts off with an interesting form for torque. It says the torque should be m hat theta in brackets kp theta minus kd theta dot plus c hat theta dot times theta dot plus g hat theta. Okay, now why do I have hats? These hats are estimates. Okay, so the manipulator has a mass, and we have a CAD model, say, and that CAD model is going to give us an estimate of the actual mass. So there's an m hat. Now, if you knew the system perfectly, and one of the goals of system identification is to find the system matrices perfectly, the mass, the Coriolis, and G precisely, then you have a perfect estimate. So we have a perfect estimate. Then m is equal to m hat, c equals to c hat, and g equal to g hat. And the system is perfectly known. Okay, so what we'll do is I'll show you what happens if we know the system perfectly. If you don't know the system perfectly, that's where the feedback controller helps us. But if we know the system perfectly, then you'll see that the equations actually reduced to a nice form. So assume perfect estimates. And now let's shove in the value for torque in the first equation. So I'm going to write that equation. I'm going to drop the m of the function. So I'm just going to write without the brackets. Okay, m theta double dot plus c theta dot plus g equals torque, which is m. I'm dropping the m hats now. Okay, so we got this. Now what we can do is we can eliminate a few things here. We can cancel off c on both sides. We can cancel off g, and we're left with this. So what we can do now is rewrite this as m. I'll pull that out, and we have theta double dot plus kp, or sorry, let me write kd first. Okay, now the mass matrix is usually not zero. Okay, so then the second term should be zero. So since m is not equal to zero, the determinant of m is not equal to zero, then we have theta double dot plus kp, kd dot plus Okay, so that's the form. Now, the beauty of this form is that this is actually decoupled linear equations. So if I expand this out, I would get something like this. That's the first term plus KD. So KD will be KD1, 0, 0, 0, KD2, 0, 0, KD3. And then same thing for KP. Theta 1, theta 2. So this whole thing equal to 0. Move this aside. Okay, so that is equal to 0, which means that we basically end up with something like this. Okay, so it's linear equation. Theta 1 does not depend on theta 2. Same for theta 2. And they keep going till theta n. Okay, so these are, as I said, linear decoupled equations. Okay, so when I say feedback linearization, what it's really doing is it's taking the non-linear terms and canceling them off. And we achieve that canceling of non-linear terms by assuming this special form for torque. It cancels off these with the actual dynamics. So the Coriolis term is gone, the gravity term is gone, the mass matrix disappears. We're only left with n linear equations. So once we have n linear equations, it's very, very easy to find the controllers which do critical damping. It's simply, the formula is simply KDI equals the same formula we wrote down earlier. It turns out that this formula is even more simpler than the previous one because you can see that M is equal to 1, C equals 0, and K equals 0. Under these conditions, the feedback controller becomes simply KD equals 2 square root KPI. And it's the same thing for each of them, right? So if you have KD1, it's 2 square root KP1, KD2 is 2 square root KP2, and so on. So this is what we get, which is a nice, simple linear controller. And once we have this controller, we can then start controlling a very high dimensional system by converting into sort of a linear low dimensional system, like a decoupled system like this. So next, I'll stop here. Next time, I will show you some, well, I'll extend this to set point control, tracking control, and integral control. And then I'll show you examples of doing this in Matlab.